Welcome to the deep dive. Today we're going on quite a fascinating journey, right inside your own body, actually.
Yeah.
We're exploring one of the most fundamental things happening constantly, but we barely notice it.
Hmm.
How your cells actually make the energy you need for everything. Living, breathing, thinking.
Yeah, absolutely vital stuff.
And maybe even more importantly, we're going to look at what happens when that whole energy-making process gets, well, cut short, suddenly, dramatically.
Right.
Our insights for this deep dive, they come from a really compelling source. It's a YouTube video transcript that gets into metabolism, specifically this condition, hypoxia.
Hypoxia, yeah. Low oxygen.
Exactly. And its role in tissue damage. So our mission is pretty clear. We want to unpack the absolutely critical role oxygen plays in your cell's energy factories and really get the implications when that oxygen, runs low.
Okay, let's unpack this. So maybe to set the stage, why is understanding this energy process so fundamental?
Yeah, great question, because it's not just like complex biology terms we're throwing around.
Right. It's really about grasping the core machinery of life itself. We're talking about the actual process, the energy production that underpins, well, everything you do.
Everything. Like
Every muscle movement, every thought, your heart beating constantly. And when that machinery falters, our well-being is hit directly, immediately.
Wow.
It's the silent foundation, really.
Incredible to think about it that way. So, okay, let's zoom in to the powerhouse, the cellular energy powerhouse, the Electron Transport Chain, ETC.
The ETC, yeah.
Now, that might sound a bit dense biologically speaking, but it's basically like the main engine in your cells, right?
Yeah.
Turning out ATP.
Adenosine triphosphate, the energy carrier.
Exactly, the body's energy money. Now, for this engine to run like smoothly, there's one thing it absolutely needs, non-negotiable. What is that? And why is it just so vital?
Okay, so what's really fascinating here, the single most important regulator, the thing the ETC absolutely, positively cannot function without, is the availability of oxygen.
Oxygen.
Yeah. Think of the ETC like a molecular assembly line. Electrons get passed down station to station, releasing energy.
Right.
And these electrons, they're carried there by, let's call them energy delivery trucks molecules like NADH and FADH2, packed with energy.
Got it. Trucks full of energy.
Exactly. And oxygen, it plays the critical role. It's the final acceptor, the one waiting at the very end of the line to take those electrons.
Oh, okay. The end of the line.
Imagine like the last handoff in a really complex relay race. If there's no one there, no oxygen to accept that baton,
The race stops.
the whole chain just backs up. And yeah, eventually the whole process grinds to a halt completely.
That relay race analogy makes it super clear. Okay, and here's where it gets really interesting and maybe a bit alarming. If we have low oxygen hypoxia, as you said, what specifically happens to this electron transport chain? Because it sounds like if that final handoff fails, disaster.
Precisely. When oxygen levels drop, hypoxia directly inhibits the ETC. It's not subtle. It's an immediate significant blockage because, well, there's just less oxygen there to accept the electrons. Simple as that.
Right.
And that immediately translates to a huge reduction in ATP output. We're not talking a small dip here.
Not just dimming the lights.
No. This is a profound impairment in the body's ability to make its essential fuel. It's like shutting down nearly all the major power grids in a city, all at once, leaving critical services and in your body, vital organs totally in the dark. The consequences are, well, immediate and severe.
That's a stark image. A citywide power outage inside us.
Okay, so if this ATP output is slashed so dramatically, it makes you wonder which parts of the body, which tissues are most vulnerable. I mean, everything needs energy, but are some tissues really on the front line when oxygen gets scarce?
Oh, absolutely. There are certain tissues we call strictly aerobic, meaning they rely almost entirely on this oxygen-hungry electron transport chain for their energy.
Okay, strictly aerobic, like with the brain and the heart, those are the big ones. Their function is directly, severely impaired when ATP drops.
Because they're always working.
Exactly. They just don't have good backup plans,
Yeah.
Good alternative ways to make the massive amounts of energy they constantly need. They need that steady, high-volume ATP supply that only the ETC provides, nonstop.
Right.
Think about, like, holding your breath, that immediate lightheaded feeling, or maybe some chest tightness.
Yeah.
That's just a tiny, tiny hint of what your brain and heart start to feel when oxygen delivery is compromised for longer.
That makes total sense for organs working that hard. Okay, so if the ETC is crippled by no oxygen, What's the ripple effect? What other, energy processes get hit immediately, leading to this massive energy crisis?
That's a really critical point. The problem isn't just at the very end of the line with oxygen. When oxygen isn't there, the whole system backs up, like we said. So those energy delivery trucks, NADH and FADH2, they can't unload their cargo.
Right, they're stuck.
They're stuck. And if they can't unload, they can't get recycled to go pick up more energy, which then halts the processes that make these energy trucks in the first place.
So it backs up even further upstream.
Exactly. The source material specifically points out 3 crucial processes in the mitochondria, the cell's power plants that get hit hard: pyruvate dehydrogenase, fatty acid beta oxidation, and the TCA cycle.
Okay, can we break those down a bit? Sounds complex.
Sure, quickly. Pyruvate dehydrogenase, it's key for processing carbs like glucose after they're partly broken down. Fatty acid beta oxidation, that's how we break down fats for energy.
Right, fats and carbs.
And the TCA cycle, sometimes called the Krebs cycle, that's like a central hub. It takes the processed bits from carbs, fats, even proteins, and churns out a lot more of those NADH and FADH2 trucks.
Okay, so all these major fuel lines feed into making those energy trucks.
Precisely. So when there's no oxygen, the ETC gets clogged. Those trucks can't unload. And so these big upstream processes, pyruvate dehydrogenase, beta oxidation, TCA cycle, they can't effectively turn the energy in NADH and FADH2 into usable ATP.
And the scale of this?
It's huge. These 3 mitochondrial processes alone account for, get this, greater than 80% of the total energy output in most tissues.
80%. Wow.
Wow. So when hypoxia cripples them, it is truly a massive, massive hit to the body's entire energy grid. Affects almost everything.
A massive hit. Not just tripping one circuit, but like knocking out 80% of the power generation.
Pretty much, yeah.
So connecting that specific blockage, these power plants going offline, what's the ultimate outcome for our health?
Yeah.
Such a huge energy deficit. What happens?
Well, simply put, when NADH and FADH2 can't be oxidized because there's no oxygen, ATP production just plummets.
Okay.
And this significant drop in ATP output, it can, and often does, lead to serious tissue damage. That's the real bottom line here. So what? Without enough oxygen, our cells just can't make the energy they need. And without that energy, tissues and then whole organs, they start to fail. They start to sustain damage that might be irreversible.
They literally starve of energy.
Exactly. Even if there's plenty of fuel like glucose or fat around, they can't use it properly without oxygen.
That really drives it home. Okay, let's zero in on one organ mentioned in the source, the brain. Absolutely critical, constantly working, incredibly complex, running everything. What does all this mean specifically for our brain when oxygen levels tank?
Yeah, the brain is uniquely vulnerable here. Its energy dependency is extreme, and its need for oxygen is just off the charts.
Why is it so dependent?
Well, it heavily relies on glucose. That's its main fuel. And it processes that glucose super efficiently, taking it all the way down to CO2 through several steps: glycolysis, then that pyruvate dehydrogenase we mentioned, and finally the TCA cycle.
Okay.
And this whole process, this complete oxidation, it's incredibly good at making energy. It can squeeze out up to 38 ATPs from just one single molecule of glucose.
38. That sounds like a lot.
It is. It's very efficient. But, and this is the crucial link we've been talking about all along, this huge ATP output is highly dependent on oxygen.
There it is again, oxygen.
Absolutely essential.
All right.
It's used right at the end in the electron transport chain, and this related process called oxidative phosphorylation. That's kind of the grand finale where the energy from those moving electrons is finally captured to make tons of ATP.
So no oxygen.
No oxidative phosphorylation, no big ATP payoff from glucose. Even if the brain is swimming in glucose, it can't unlock most of its energy without oxygen.
It has backup systems, right? Or
It does have some, but they are much less efficient. They just can't keep up with the brain's massive energy demands for very long at all.
So it really is a perfect storm for the brain, isn't it? Huge energy need, a specific pathway it loves, and that pathway absolutely needs oxygen.
That sums it up perfectly. The brain is truly on the front lines when oxygen becomes scarce.
And the consequence?
If we experience hypoxia, the consequence for the brain is a significant, really rapid decrease in ATP, which directly and very quickly results in tissue damage.
That fast.
That fast. The brain just cannot sustain its complex functions, thinking, controlling your body, everything, without that constant high-level energy supply that oxygen makes possible. Even just a few minutes without oxygen can cause permanent damage because this whole energy production system shuts down so quickly.
That's really sobering, understanding how fragile such a vital organ is.
Okay.
So let's recap our deep dive today. The essential takeaway seems incredibly clear.
Hmm.
Oxygen isn't just, air we breathe. It's the critical igniter. For our cell's main energy factory, the ETC.
The spark plug, maybe?
Yeah, good one. And this process is vital everywhere, but especially for those strictly aerobic organs, like you said, our brain, our heart.
Absolutely.
There's this direct, undeniable link. Oxygen availability connects straight to ATP production, which connects straight to the health, the function, the actual survival of our tissues.
It really is that direct. And it really raises an important question for you listening out there, doesn't it? About just how incredibly intricate and yet how perfectly balanced our body systems are. We tend to take something like oxygen totally for granted, right? Just breathing in and out, no second thought.
Yeah, completely.
But as we've explored, it's utterly non-negotiable for our internal machinery to actually thrive. It's just a profound reminder, I think, of the delicate balance that sustains our life. And maybe it encourages us to appreciate these miraculous internal workings keeping us going, every single second.
What a thought to end on, that delicate balance. Thank you so much for joining us on this deep dive into the fascinating and pretty critical world of cellular energy and oxygen.
My pleasure.
We really hope this has sparked some curiosity for you to maybe explore a bit more about how your own incredible body works. We'll get you next time on The Deep Dive.